Hello and welcome to another video. In this video we're going to be working on minimum height trees. And in this problem you have a tree which is an undirected graph. So basically what a tree is it's an undirected graph that every node is connected and has no cycles. So you're always going to have, if you have n nodes, you have n minus 1 edges. And this is always going to be true for a tree. So, and then everything will be connected. So like here we have 4 nodes, 3 edges, and so on. And basically what they tell you is given some kind of like connected structure, like these are all the same thing, just drawn differently, right? Like the ones in the middle, and then it's surrounded by these. Return every single node from which, if it was the root of the tree, would give you the smallest height of the tree. And so the height is calculated by, like, if this is the root, it's just the path down to the leaf. So, and I believe the way that height works is, I mean, you can do it a few ways. You can say, like, this is the bottom level is height 0, and then every level above that is 1, 2, 3, and so on. Or you could say the bottom level is height 1, and everything's like 2, and so on. Either way, but let's just say the bottom level is height 0. So basically, here, like, this is all the same way. This is like all the different ways of drawing one thing. But there's only one node that can be the height of the smallest tree, because I guess it's not. So if zero was the root, then this would be like height 0, height 1, height 2. So that would be a tree of height 2. Here we have height 0, height 1. So I guess we can leave this as 0, 1, 2, 0, 1, 2, 0, 1, 2. So 1 is the only one that could be the root of a tree of height 1. So this is going to be the tree of the smallest height. So then you want to just return 1, because no other node can be the root. And in this example, same kind of thing. So this is height 0, height 1, height 2, height 0, height 1, height 2. So you could use either 3 or 4 as the root. And if you were to use something else, like let's say we used 5, well then if 5 was the root, then this would be like let's think of how far down we can go. Well, this would be height 0, height 1, height 2, height 3. So that wouldn't work. What if we used like 1 as the root? Then this would be height 0, 1, 2, 3, and so on. And so basically, and this would be height 2 as well. So, and this would be height 2. So the only nodes that can be the root are the nodes that give you the smallest height. And you want to try to do this, and the constraints are not super easy, so you can't have something n squared. So something really easy you could do is you could just BFS from every single node as a starting node. But this would give you a TLE, but let's say the constraints were a little bit smaller. So for example, we can BFS from here, and then we can just figure out like what's the furthest node we reach and what's the longest path, and that's the height of the tree. So like this will be, distance 1, distance 1, distance 1, distance 1, distance 2. So then the height is 2. And then if we used 5, it would be like distance 1, distance 2, distance 3, 3, 3, right? And so on. So basically you could do a BFS from every starting node, which would be an n squared solution. And then the nodes that give you the smallest, like maximum distance traveled, would give you the answer. But we can't do that. But what else can we do? Well, for a tree, like basically we have to ask ourselves, like, what determines what can be a leaf of a tree? And so in order for something to be a leaf of a tree, it has to have no children, right? So a leaf of a tree has 0 children, 1 parent. And so if we take a look at like this example, or if we go back to this previous example, what nodes can be a leaf? Well, this node can be a leaf, this node can be a leaf, this node can be a leaf. This one cannot because it has 3 connections. So basically any node with 1 connection can be a leaf. And those are going to be the worst nodes to pick for the height, because a leaf to leaf distance is usually going to be like the farthest path in the tree, right? Like if you just have a normal binary tree, for example, like let's just say we have this binary tree. So typically the longest path in the tree is actually going to be 1 leaf up until the root down to another leaf. So the nodes you want to pick as the root it's like the center of the tree. Like if you're like, this would be like the center of the tree. So that's kind of the idea, is like, imagine you have a bunch of like layers and you're peeling off layers, and then whatever's in the middle is going to be your root, because that's going to be like, the least height to everything else. And in this picture, you can kind of see that. So you can see like this is in the middle, and then there's a node on each side. So this is the one you'd want to pick as the root. So that's kind of the same idea here. Is basically what you're going to want to say is you're going to want to say like, okay, what can be the leaves? I'm going to peel off those leaves. Then what can be the leaves? I'm going to peel off those leaves and so on until you have a few nodes left, and that's going to be your root. So let's actually go through that in these examples. So like here, the nodes can be leaves are this node, and this node. And now we just have this, which is our root. In this example, the node that can be the leaf is this node, this node, this node, and this node, right? Everything with a parent and no children. Now we have these two nodes left, so 3, 4. So these are going to be our like answer, because they are like, you can't peel off one without peeling off the other. So basically, your answer is when you only have nodes that can be leaves left. And if we do that from like this view as well, we peel off this, then now these nodes can be leaves, right? Because for 3, 4, these nodes only have one connection and no children. So basically, you just keep doing this and you keep doing this. So let's take a look at this example that I made. So here, essentially, we're going to look, okay, what nodes can be leaves? So it's going to be this node, and this node. Now, what nodes can be leaves? So if we just like delete all these, so bye-bye to these. Now what nodes can be leaves? Well, it's going to be this node and this node. And now these two can both be leaves, so this is our answer. So 1 and 2, and if we actually go back and we calculate heights from every single node, so the maximum height, like I said, is usually going to be leaf to leaf. So for example, this 6, the maximum distance is going to be like 1, 2, 3, 4, 5. So the maximum distance here is 5, so that's going to be the height. Then here it's going to be, so 1, 2, 3, 4, 4, 1, 2, 3. So this way, right? 1, 2, 3, 3. And you can kind of see that there's like this recursive thing, right? This has maximum height of 5, 4, 3, and so on. This is 2, this is 1. These are both 0. Actually, sorry, this is wrong. So the maximum here is 3. Yeah, 1, 2, 3. So that's true. But this is not 2. Because from here, you can go 1, 2, 3. This is 3. Now this is not 0. This is 1, 2, 3, 4. And now this is 1, 2, 3, 4. And 1, 2, 3, 4, 5. So you could see the trees with the minimum maximum height are going to be these two. So that's kind of your strategy, essentially. You just peel off things that can be a leaf until you only have nodes that are leaves. And then those nodes are your answer. But how do you do this in code? So the way to do it in code is pretty simple. We make this graph, and then all we need is an in degrees array. So let's show what that's going to look like. So for every single edge connecting something, we just raise the amount of in degrees we have. And in degrees just means like how many edges are connected to this node. So 0 only has one edge. So this is 1. 1 has 3. 2 has 2. 3 has 2. 4 has 2. 5 has 1. 6 has 1. 7 has none. Okay, I guess these don't exist. So then what you do is you take everything with an in degree of 1 and you can put that into like an array or a queue or whatever. We can just use an array or like a list. So what indices is that? That's going to be 0, 5, and 6. Then these are our nodes that can be leaves. Then we'll make another array of our next leaves, like once we get rid of these. So for 0, we're going to go through all of its children and lower the in degrees by 1. And then if that in degrees is 1, then we'll put that into our next leaves. So we're going to get rid of the 0. This goes to 2, right? Because we got rid of this node. So now 1 only has 2 in degrees. Then we get rid of the 5. So get rid of the 5. Now this 3 has in degree of 1. So we can put it into our next leaves. And then we get rid of the 6. So 6. And now 4 has an in degree of 1, which we can put in here. So now our new leaves are these. And then we can kind of just like move this around, and then we have a new array that we do again. So for 3, it's connected to a 1, so we get rid of the 3, and we lower the in degrees for 1. So now 1 has 1 in degree, and which means it's going to go into here. And then for 4, we're going to get rid of it as well, and we lower the in degrees for 2. So now 2 has 1 in degree, so we're going to put in 2. Get rid of this. And now if we look at the children, or I guess what's going to happen here. So what we're really going to do is we're going to have two arrays. So we'll have an array of like our current batch and then our children. So when we try to get rid of these, we're going to say, okay, let's get rid of 1. Now the int degrees for 2 is 0, but we only put in things with an int degree of 1. Then we get rid of 2, and then that's it. And then 2's children was 1, so the int degree for 1 is 0, but we only put in things with an int degree of 1. So now because our next batch is empty, that means our current batch is our answer. So essentially we have like a current level that we're like peeling, and then we have our next level. And then if the next level is empty, then our current level is the answer. And we just keep doing this until we get to an answer. So that's basically it. We just keep track of int degrees to figure out where our leaf nodes are, and we keep peeling off the leaves until there's only one level of leaves left. So let's code that. See how much code it is. So what we need is we need a graph where the key is a integer, and then the value is a list of integers. So let's do that. So it's going to be like map integer list integer graph. This is going to be a new hash map. Yeah, definitely for these graph problems, using Java is still reasonably annoying for me because I'm not used to it. So essentially now what we... Oh, so by the way, there's an edge case here. So there's one edge case where you have just one node. So if we have like 0 and we have no edges at all. So we can just return there. So if n is equal to 1, there will be no edges. So we can just return an array. This is going to be... let's see. So we basically need to return a list of integer of just one value. So I think this is going to be like new list integer or new array list or something. Let's see. Array list. I guess we can make it first. So we can say like list integer to make it really bad. So like this equals new array list. We can make it up here. So we can call this and use it. So this can be like our level. And then we can just return that thing. So we can say like level dot add 0 return level, something like that. Okay. So yeah. So then basically what we need to do is for our graph, we need to go through our edges and add to the graph. So we can say, so our edges are just two things. So it's going to be like an int array edge and edges. And basically we need to add the second edge to the first edge's graph and the other way around. And we also need to increase the int degrees. So that's the other thing we need to make is we need to make int degrees. So let's make int degrees. So this is going to be, you can just use an int array here, int degrees equals new int array. And the length of it will just be n, because every node has an int degree. So yeah. Okay, so first we have to actually increase the int degree of both of the edges. So this will be like int degrees. We can make the integers here, so we could say like int x equals edge 0, int y equals edge 1. So we could reuse it. So we could say int degrees x plus plus int degrees y plus plus. Now we have to add to the graph. So we have to say graph dot. So I believe this is like put if absent x. So here we need to make a new list. So this is just going to be new array list. Okay. So basically if this key doesn't exist, put in a new list. Same thing for y. Now we need to add them to it. So we can say graph dot get x add y graph get y add x. So now we have our graph. Now we need to create our first level, and then we need to be like doing these peels. So we can say for int I equals 0, I is less than int degrees length. So essentially everything that has an int degree of 1 should go into our first level. So if int degrees I equals 1, we need to put it into our level. So this is going to be level add, and we need to add the index, right? Just the node. Okay, now we can have, so I think the way I had it before was just do an infinite loop, so I'll just do that. So we'll just say while true. So what we need to do is we need to make a new array of, or a new list of like next level or something. So we can just do this. So we can say integer next level equals, yeah, new array list. Then what we need to do is we need to go through our current level, and then for every child of our current level, we need to subtract its int degrees by 1, and then if it's a 1, we need to add it to our next level. So this is going to be, and in order for a node to be in our level, like if it's in here, it's always going to be connected, so it's always going to be in the graph because it's a tree. It doesn't have cycles or anything. It doesn't have like islands. So we can say if, or not if, for int child and graph get, actually sorry, before we need to do that, we need to loop through every single node in our level. So this is going to be for int node in our current level, so level. Now this is going to be for int child in graph get node. So this is going to be in degrees. We need to subtract it, right? So essentially for our current level, like our picture before, basically what we're doing is we are deleting this node, which means the in degrees of every node next to it goes down by 1. And if the in degrees becomes 1, now it can be a new leaf. So in degrees child minus minus, if in degrees, and we don't need a visited set or anything because this will basically only happen once. Like we only put something in when its in degree becomes 1 after deleting a parent. So that can only happen once. So if in degrees child equals 1, then we add it to our new level. So next level, add child. Basically it, I believe. Now there's a couple more things. So now after we go through all of our like level, if our next level is empty, we should just return our new level or our old level, right? That's kind of like the case here. Like what's going to happen here is like we'll delete all these to start off, and then our level will just be these two, and then our next level will be empty. So we can say if next level size or is empty, then we can just return our current level because that's our answer. So return level. Yeah. Otherwise, we just keep going. But before we keep doing, we have to reassign current level to be next level. So we can say current or level, I guess, equals next level. Like this. And then when we make it again, it's not going to have the same address because we make a new one, I believe. Yeah. And so technically this loop will basically never break. It will always return before breaking. But we can just return something if we want to. Like we can say like return level or something if you're doing a language that requires a return value. But this will basically never be hit. Oh, I guess it... Oh, yeah, it tells you it's unreachable. Okay. Yeah, so we never break, so it'll just be this. Yeah. There we go. Like, there's probably a better way to do it than while true. While true is usually not the best thing, but this is kind of the idea of it. So essentially, we're just peeling off levels until we have one final level, and that's our answer. And so, time-wise, so this is basically O of n, because essentially, so I guess not technically O of n, but to make the graph, so you can actually do this in terms of n, because for a tree, like I said before, the number of edges is n minus 1. So the number of edges relies on n. So to make the graph is O of n, because the number of edges is n minus 1. To make the int degrees is O of n. This is all, so this whole thing is O of n. Then traversing nodes and their children, basically we're going to traverse every node one time, and then we're going to check its children one time. So all the children together will add up to, I mean, it won't add up to the tree exactly. I think it'll add up to like 2 times the tree or something, because you can have like you know, you can have multiple connections. But either way, that's O of n. So essentially, this loop here is O of n. So the whole thing is O of n, space. So for int degrees, obviously O of n. For the levels, that's also O of n. It's pretty hard to picture. Like, I can't really picture a tree where everything's elite. I guess I could, right? But yeah, it wouldn't really matter. So basically where everything's a leaf would be like this, and then everything just connected like that to it, right? So let's say you have a tree of like, you know, a million things. It would basically be like this would be the center, and then every node would just be one away from it. Something like that. And then your first level would be everything. So something like that. So yeah, this is O of n. And yeah, kind of a weird graph problem, kind of a weird tree problem. Like, this is pretty rare, but that's the main thing to recognize here is, I think it is kind of intuitive looking at the pictures that to have the min height, you want to kind of be in the middle of the tree, but it's kind of hard to figure out like how to actually get to the middle of the tree. And the way to do that is just peeling off leaves until you get to the center. So yeah, it's going to be all for this one. Hopefully it was helpful. If it was, please like the video and subscribe to the channel. And I will see you in the next one. Thanks for watching.